The biggest moneymaker in mathematics is when you've got equations that you need to solve for some kind of applications. And instead of solving those exactly, which a lot of times you can't even possibly do, you approximate the solutions. So people have been doing this for many, many years, hundreds, thousands of years. But now that we have computers, we can do it extremely efficiently. So we have tons of ways to make approximations for solutions of equations. Um, I'm going to give you a really simple way today that's called Newton's method, developed by Isaac Newton several hundred years ago. It's a fairly simple method, um, and it's easy to understand, so I think it's a good first taste at an approximation method. I'll give you the theory of how the method works, and then I'll make another short video to give an example. Here's how it works. You've got your equation that you need to solve. So you've got a left side and a right side of the equation. Take that equation and move everything over to one side so that one side of the equation is equal to 0. Once you have that, take the non-zero side and call all of that f of x, or just call it some function name. If you think of it as a function, then you can look at the graph. And let's say that the graph looks like this. If you approximate where you think there might be a solution, or you just pick a random number, then that gives you a point on the graph. So I'm going to call it x1, but you would pick a specific number like 2 or 5 or something. When you plug it into your function, you get a y value. It gives you a point on the graph. And you can look at the tangent line to the graph at that point. And look at what happens. If you follow the tangent line down or up toward the x-axis, then where it hits the x-axis can take you closer to the solution for the equation. Now remember, the equation says your function is equal to 0, so you're trying to find where the graph hits the x-axis. You're trying to approximate the x value where the graph hits the x-axis. So if your graph looks like this and you follow the tangent line, it takes you to a point on the graph that's closer to the actual x-intercept of the graph than the x value that you started with. Now, I will tell you that this method doesn't always work, but it's especially nice when you're working with polynomial equations or fairly simple equations. So we've got this point x1, y1, and we know how to get the equation of the tangent line from that. We'll use the point slope form of the line. Y minus y1 equals slope times x minus x1. And we know the slope of that line is the derivative of the original function, and we'll plug in the point x1 into that to get the slope. So we've got y minus y1 equals f prime of x1, that's the slope, times x minus x1. And now on that tangent line, we want to see the exact point where y is equal to 0. And let's call the x value on that tangent line where y is equal to 0, let's call it x2. So x2 will be our second approximation to the actual solution. So then if we plug in y equals 0 and x equals x2, we get 0 minus y1 equals f prime of x1 times x2 minus x1. And we know what x1 is, so we can fill in numbers for all of this except for the x2. We don't know what x2 is. So let's just solve the equation for x2. Divide both sides by the derivative, and then add x1 to both sides. So then we get x2 is minus y1 over f prime of x1 plus x1. In nice situations, that will be closer to the actual solution than the original approximation that we gave. How much closer, we don't really know, but the cool thing is that we can keep doing this over and over and over. So now if we look at x2, calculate y2, that gives us a point on the graph. And then we can look at the tangent line there, and that tangent line will take us toward the x-axis, and it will hit the x-axis at another point that's even closer to the actual solution to the equation. So we'll get a better approximation. Let's call it x3. And then you can keep going. You can get an x4, x5. You can do this as many times as you want. You can feed an algorithm to a computer. You can write a program so that it will calculate this over and over. And you can tell it how long you want it to spend on the problem. And it can get you a really good approximation really fast. So if we look at x3 now, the equation for the tangent line at x2 is really similar to the equation that we just used for the tangent line at x1. It's the same equation, y minus y2 equals the slope times x minus x2, and this time the slope is f prime of x2. And now we're going to fill in y equals 0 because we're down at the x-axis, and x3. So we get 0 minus y2 equals f prime of x2 times x3 minus x2. And when we solve that for x3, it looks just like the equation that we just got for x2. For that one, we had x2 in terms of x1, and for this one, we get the same thing, but x3 in terms of x2. And so you can do this for any level of approximation that you want. You can continue this as many times as you want. When you get to the nth approximation, xn is just going to be equal to negative yn minus 1 over f prime of xn minus 1 plus xn minus 1. That's the theory, and I will make a video giving you a nice example, a nice simple example of how you can work this out. You wouldn't want to do this much. You wouldn't want to do many steps here by hand, but again, a computer can do it really nicely, and that's really the whole point of this in modern day. Back in the day when Newton developed this, it still was really useful for him for applications, and people developed all kinds of approximation methods like this, even though they didn't have computers to crunch the numbers quickly. But now that we have computers, it makes things so much easier, so much faster. So really that's one reason why technology has been able to develop much more quickly.